Conservation of momentum, page 69 on your Cornell's notes. Alright, what do you mean by the word conservation? Every time you see this in our previous lessons, we already had two laws of conservation. That means that the quantity is being conserved, it is not changing. So, what are the conditions that will tell us that our momentum is not changing? Okay, first of all, let's review. Yesterday we talked about momentum and impulse. And for an object to accelerate, there should be an outside force applied to the object. This outside force over a period of time is called impulse. And this is the reason why your object changes in velocity or accelerates, and then you will have a change in momentum or impulse. For the conservation of momentum to be applied, though, our force applied to the system should be internal. An example for that force is, say for instance, you're inside the car is moving, you try to push against the dashboard. That force from your hand to the dashboard is considered internal, and it doesn't really affect the total momentum of your moving car. So we say that internal forces like these are balanced and just cancel out. And if there is no other outside force present in the system, then the momentum of that object will remain the same. Now let's take a look at two objects that are interacting. For the law of conservation of momentum to be applied, normally the situation is during collision or explosion. Remember that the two objects here are only changing or transferring their momentum to the other object, and in that case we consider all those forces as internal. The only external force that will affect the system in this case is friction, so we will neglect friction for the sake of the law to be true as applied to our problem solving. So here's the basic equation for the law. Total momentum of objects A and B, two objects all the time before collision, should be equal to their total momentum after collision. The total actually refers to the sum. Okay, so if you see apostrophe on the right side of your equation, that refers to the momentum after collision. Alright, so what are the two types of collisions? The first one is elastic. This happens when objects separate after collision. So we have three situations here. The first one, here's the second one, and the third one. In all cases, momentum is only transferred from one ball to the other, so the total remains the same. The second type of collision is what we call inelastic, meaning the two objects stick together after collision. The red card and the white card stick together. They now have the same velocity and their masses are now being added. So from these two types of collision, here's an example, a good example of elastic collision, the Newton's cradle. Notice that the objects are, the marbles are separated after collision. Alright, now so for expanded equations, which we will use for our problem solving, elastic collision, momentum of A, which is P sub A, is now expanded as M times V, because remember P equals M times V. So M times V of A is the momentum of object A plus the momentum of object B before collision, and right on the right side is the after collision with the apostrophe. For inelastic collision, notice that on the right side we have a different equation here, because the masses A and B after collision stick together and both of them will now have the same speed. Let's apply these equations for our problems. So the first sample problems for the elastic collision. How would you know which is A and B? This is how I do it. The first kilogram stated is what we normally label as object A. So that's the reason why I put MA here, which is 0.015. the second kilogram stated will be labeled as B. Now take note also of the phrases after and before collision. So the after collision numbers here will go to the right side of your equation. So you need to draw step 1, draw carefully, label how you picture out the statement of the problem. So here it is. Very important. If the direction of the object is to the right, velocity is positive. If the object is going to the left, velocity is negative. If you miss these signs, you're going to end up with the wrong answer. Alright, so after you label step 2, we are now ready to write down our general equation. So since this is an elastic collision, we copy the general equation from the previous slide, this long equation here. In the step 3, we will encircle the unknown. Since we're looking for the speed of the second marble after collision, that would be the V prime B. Second marble, which is B, after collision with the apostrophe. So any other variable next to the unknown need to be moved to the left side of the equation. Notice that we will move first MAVA prime, and we will normally move the variable next to the unknown last. So when you move MAVA prime to the left, it is positive, it will become negative. When you move MV prime to the left, it's being multiplied, it will become divided by. So here's the equation now for VB prime. Remember, in this problem set, we won't have any formula chart, so you need to learn how to rearrange your equation. So substituting the numbers from your drawing to your equation here is really easy. Just make sure that you take note of the negative sign, and here's one for the VB, and here's another one for the VA prime. Okay, when you plug this in your calculator, it will exactly look like this. Open parentheses and make sure that you're using the common multiplication sign. Now this will total into 20 meter per second positive. That means that the second marble will be going to the right. Okay, let's look at our last example. In elastic collision, we have two fish, the 2 kilogram and the 6 kilogram. So on your drawing, since we have 2 kilograms stated first, and it is a negative number, that means that is your first object. So we will label that object A, and negative means it's going to the left. So that's why I put that in the drawing. This fish is going to the left, and the larger fish, which is 6 kilogram, is stated second here, so it will be labeled B, and is going 3 meter per second, so to the right. After collision, the small fish actually swallowed that big fish, so now the small fish and the big fish inside its belly will have the same type of speed, and we're going to add both their masses, and this is the variable that we'll be looking for. Alright, so step 2, we determined that this is an elastic collision, so we copy the equation from the previous slide, and we encircle the unknown for step 3. Okay, so MA prime and MB prime is not encircled, it will be moved to the left side of the equation. Since this is multiplied, when you move it, it will be divided by. So this is the whole equation for VA and B prime. When you substitute and you follow the signs of the velocities on your drawing, you should get a 2 meter per second positive to the right. I hope this helps. Use this for the next problem for your pages 70 and 71 worksheets.